with um, with the bases and the transition matrix ideas and all those kinds. So we can start with that. We can go our way backwards if you want. We can start with the harder part stuff and then go. This is more simple, basic understanding of vectors. Probably the most difficult part here would be the orthogonal projections. Okay, so someone suggested number 11.
Maybe I misunderstood because I asked you the same question on Monday and you said it was just the R and the S values.
The R and S values.
Because this one's just finding the row reduced echelon form of it and then you're making that into x1, x2, x3, x4, x5. And then creating a non-zero vector of that null space.
Yeah, give a non-zero vector. That's right. So the thing is, most likely, and yes, the null space will be a dimension higher than. So there's going to be an infinite number of things in the null space, right? So let's look at number 11. So part A, I mean, A is a given matrix, and your matrices may be different. And we want to find, so it says give a non-zero vector x in the null space. Of A. So the idea is you want to find the row reduced echelon form of A. Why is that? Well, one reason why is this is a 3x5 matrix. And remember what this matrix represents. This matrix represents the coefficients of a linear system, right? That has 5 variables. So you can always reformulate all of these rows as equations, right? Negative 2x1 plus 5x2 plus 5x3 minus x4 minus plus x5, that equals 0. So when you find the row reduced echelon form of this, it tells us the number of pivot variables, the free variables that exist, and so on. So inherently, when we're finding the row reduced echelon form of a matrix, you're inherently solving the system of a homogeneous system. That's what you're inherently solving. So that's what I'm going to do. I'm going to plug in my matrix. So it's a 3x5, and I think I have it. Yep. So I have it already placed into my matrix, and then I'm going to row reduce echelon form this. So for the test, for the exams, you don't have to do it by hand anymore. You don't have to do the whole thing by hand. You can just use your calculator function and make it do it for you. And I'm going to do math enter. Okay, so this is my matrix, the row reduced echelon form. I get 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I get 1, negative 2/5, 3/5, negative 4/3, 3/10, negative 19/30. What are the buttons for row reduced echelon? Yes, that's a great question. Yes, these are things you should know. So first of all, you have to have a matrix to deal with, right? So you have to edit the matrix and then input the values. So then once you have it, you can always refer to them right under names. So then to find a row reduced echelon form, you go again to second matrix, right? Which is this here. So if you go to the home screen, you go second, and then you go to the x to the negative 1 power, which is matrix. And you go under math. Under math, you have all these different operators that you can apply to the matrices. All of these are operators that you can apply to matrices. So you can even find the dimension of certain things here. You can augment, but the most of the things that we deal with in terms of the functions here are determinant. We have used the transpose sometimes, but we mostly use the determinant. And if you go to the bottom of this, you have row echelon form and row reduced echelon form. So it's math, and then you go to this B option and press enter. And then once you have that, then you can specify again what matrix you want. So you go back to the names of the matrices, and I want the A one. So I press that, I close the parentheses, and then boom, it gives me the row reduced echelon form. And then I notice I have these like repeated decimals. So then what I do is I want to find the fraction version of it. So I go to math and go to 1. So it takes my answer and makes it into a fraction. So boom, I got it. Yeah. So the determinant, so all those things that we've seen the calculator version of it, you can use your calculator for. So I don't expect you on this exam, if you have to calculate the determinant, what to see whether or not a system is consistent, meaning that there's a solution. Finding the determinant using the calculator would be perfectly fine. I would not expect you to use to calculate determinants by hand any longer for the exam, unless I specify find a determinant by hand. But on this exam, you're not expected to find a determinant by hand. You're expected to do other things. So putting a matrix in row reduced echelon form, you don't have to use by hand for this exam, nor do you have to find by hand any determinants of any matrices. Okay, because this exam is not so much focused upon the computational aspect of it, of linear algebra, but more on the conceptual. So for example, you can do this by hand, but no, it's not necessary. The more important thing that I'm trying to share here with you is the significance of these numbers. Because you can get to this point here by hand, but if you don't know what these things mean, it doesn't really matter much, right? So what does this give me? What does this give me? Well, this helps me in solving for the null space, which is the set of vectors that make my matrix when you multiply, right? When I multiply by the vector in the null space, I get 0, right? The 0 vector, and the 0 vector here is representing a homogeneous system of equations. So then with this in mind, this row reduced echelon form gives me what? X1 plus X4 minus 4/3 X5 equals 0, right? That's the first row, row 1. Row 2 gives me what? X2 minus 2/5 X4 plus 3/10 X5. This also equals 0. And then lastly, X3 plus 3/5 X4 minus 19/30 X5 equals 0. Do you see that? And what do I notice? What should you immediately notice? 3 pivots. And what are the pivot variables? X1, X2, X3. What are the free variables? We got 2 free variables. x4, x5. So x4, x5, which are associated with these two column vectors here, are the free ones, right? And so normally we associate them with letters. So we call this S, for example, and call this T, or you can use anything, R, anything. So when we solve for x1, x2, and x3, I get negative x4 plus 4/3 x5. I get x2 is 2/5 x4 plus 3/10 x5. Pardon me, it should be minus. And then x3 is negative 3/5 x4 plus 19/30 x5. And x4, I call it S, and x5, I call it T. Now remember, what are these? x1, x2, x3, x4, x5. They're the components or the entries of my vector. So it's x1, x2, x3, x4, x5. I'm trying to look for all the vectors that when I plug it into this system, I get 0. That is what I'm looking, that's what I'm looking for. So then all I'm going to do now is, instead of writing x4 every time, I'm going to write S. And again, this is just renaming the stuff, the variables here, which is not so significant. And then x5, I'm going to call them T's. Everybody with me so far with this? The row reduced echelon form of this? Yes? Okay, so then once we have that, instead of writing x1, I'm going to write what? Negative S plus 4/3 T. Instead of writing x2, I'm going to write 2/5 S minus 3/10 T. And I'm going to have negative 3/5 S plus 19/30 T. S and T. But as you can tell, I can separate this, right? I can separate this as a sum of two vectors where one vector includes all of the S's, that only the S's, and the other vector has only T's in them. So this becomes negative S, 2/5 S, negative 3/5 S, S0. This vector, I add it with this vector, 4/3 T, negative 3/10 T, 19/30 T, 0 T. Since all of this vector, first vector has S's in them, I can take out the S. I'm left with -1, 2/5, negative 3/5, 1, 0. Take out the T and I'm left with 4/3, negative 3/10, 19/30, 0, 1. Now, what is this? What is this? What did I find? I found the general solution. I found two non-zero vectors. So I found several things, right? I found the general solution to what? This is the general solution to what? To the homogeneous system. The key word, guys, is the homogeneous. Now, why is it called a general? Why is it not particular? The reason why is because T and S are not defined. The moment I define what S and T are, like I determine what numbers they are, I get a particular solution to the homogeneous system. And these are exactly non-zero vectors that do what? They form a basis of the null space. So the null space of A, is described as the span of the vectors -1, 2/5, -3/5, 1, 0, and 4/3, -3/10, 19/30, 0, 1. Do you guys understand this? Why is this the null? Why is this the span? Because I found what the x is, right? I found what x was. What is x? X is the solution to this equation. That's what x is. That's what I found. I found the solution to the homogeneous system. I found it. It's this. But when I notice is, hey, look, this is also expressed as a linear combination. This is it. The way we write this is a linear combination. So this x, which is solved in its general form, right? This x vector is a linear combination of these two vectors, which means that the null space is the span of these two vectors. So then the question is, find a non-zero vector in your null space. Well, you can take this to be your null, you can take this vector to be your non-zero vector in the null space, because that's what it is. I can make this a 0 and I can make this a 1, and then this becomes a part of the null space. I can make this a 0 and make this a 1, and this is my non-zero vector in the null space. Or I can write any linear combination of these two vectors, and this will be another non-zero vector in my null space. There's an infinite number of vectors in my null space determined by S and T and by these two vectors. Does that make sense? So the answer to this question, there's an infinite number of ways. So let me just say this also, because these are linearly independent. These are linearly independent. So this is a linearly independent spanning set. So it's a basis for a null space. So they constitute a basis. Okay. So either one of these vectors should work. Either one. And if you don't want to deal with, like, I don't like sometimes dealing with fractions here, I can just find a scalar multiple of this vector. So like 1, -1, 2, 5, -3/5, 1, 0. I can just find a scalar multiple, multiply everything by 5, for example, and I get -5, 2, -3, 5, 0. So this is a non-zero vector that's in the null space. This is in the null space of A. So just a few things from here that we can additionally add. What's the nullity of A? What's the rank of A? Right, so the interpreter is right. Nullity is 2 because the dimension of null space is given by the number of elements in your basis. So if this is a basis for the null space, then your dimension is 2. What about the rank of A? Nullity equals col minus the row. Not quite, Tassif. So the rank nullity theorem, which is a very important theorem, the rank nullity You have to be careful with that. It's not that it's the row, it's the rank. That's the only mistake you have. So the nullity is equal to the number of columns minus the rank. Minus the rank, not minus the rows. Because you can have a rank of a matrix that's smaller than the number of rows. So that's the only difference. So in reality, you should always think of it as rank of A plus the nullity of A equals the number of columns of A. Or in other words, Rn, right? This is usually, we define this as N. What's the formula for the rank? That's an excellent question. Well, then the question that can be equivalently asked is, how do you find the rank? And that question is similar. The answer to that question is similar to saying, how do you find the null space? Or how do you find the nullity of A? So remember, all of this is going back. The number of pivots. Well, the number of pivots tells you the rank of A. But how do you find the pivots? How do you know the number of pivots? Right. It's the row reduced echelon form. So you see, we're going back to the beginning. We talked about the row reduced echelon form, but we talked about it from a technical aspect. We talked about the procedure of applying the Gauss-Jordan elimination, which is the elementary row operations upon a matrix, and we get our desired matrix, which is a row reduced echelon form. But now we're coming back to it with much more. There's much more information to come to glean off of the row reduced echelon form. Now we're talking about, the null space of a matrix. Now we're talking about the row space of a matrix. Now we're talking about the column space of a matrix. Now we're talking about spaces, vector spaces, subspaces, which is much more conceptual than when you first were presented with the idea of row reduced echelon form. So there is no formula per se of finding the rank of a matrix A, but there is a procedure, which is to find the row reduced echelon form. So once you find a row reduced echelon form, that's why I wrote this stuff out, because immediately it should give you a lot of information beyond just the numbers inside the matrix that constitutes the row reduced echelon form. This tells you the pivot variables, or which come from the leading ones. The leading ones, the number that you see, the number of leading ones that exist in the row reduced echelon form constitute the rank of the matrix. And then once you can find the rank, you can find also the nullity, which is the number of free variables. And if you add the number of the rank plus the free variables, it should give you the number of columns, which deals with the codomain of the linear transformation. Okay. And then on top of that as well, on top of this, the row reduced echelon form, in addition to giving us all that information with the rank, the nullity, it also tells us which column vectors are linearly independent, which row vectors are linearly independent. So it looks like every row here is linearly independent with one another. So these row vectors are a basis for the row space of A. So if you want to look at the row space of A, take these three vectors and take any linear combination. Take the span of these linearly independent vectors and you create the row space. And then if you look at the column version of this, it's saying that the first three here are linearly independent. So if you take these three vectors, they're linearly independent. And if you notice, these are column vectors in the world of R3, right? There's the three components in each of these column vectors. So they create a basis for R3. And you can think of A, right? What is A? A is representing A represents a linear transformation. Don't forget about that connection. Represents a linear transformation, called a T, and T goes from R5 to R3. So these columns here, these column vectors are a basis for R3, and these row vectors are a basis for the subspace of R5, which is the row space. Okay? So I should say this. The row space of A is a subspace of R5. And the column space of A is also a subspace of R3. But because these three column vectors here are linearly independent and they span R3, because you have three vectors that are linearly independent, you immediately have a basis for R3. So column space of A in this case is actually all of R3. The column space of A is all of R3. But the row, pardon me, but the row space of A is merely a proper subspace of R5. Because in order to be in a all of R5, you would need to have 5 vectors. Here we only have 3. Okay, does that make sense? So the column space of A is all of R3, but the row space of A is only a portion of R5. So any questions about this particular problem from the homework? Does everybody now, is this clear with how significant the row reduced echelon form is and how that helps us find vectors in null space? Does that make sense, guys? Anything else from, yeah, number 6. Oh, we have time. I think we have plenty of time. So number 6. Again, my numbers here might be a little different. Okay, so number 6, right? We're dealing with the subspace P2. What is P2? It's the set of all sometimes you guys are used to seeing this A plus BX plus C. It doesn't really matter. Hopefully now you start to see it doesn't matter, right? It's the set of all polynomials of degree less than or equal to 2, where A nod A1 and A2 are all constants or real valued constants. And you can write this the same way as this, right? This is just an equivalent way. That's what P2 is, right? Equivalent. Okay, so one way that we sometimes treat polynomials in this space are as vectors with 3 components. And what we have 3 different bases. We have 3 different bases. The first is called B. We have a basis called B. We have another basis called C. And then we have another basis called E. Okay, E is the standard ordered basis for P2. Oh, well, actually, yeah, this is the one where I said that they had a typo. This should be called P1, not P2. It's called P1 because the degree is actually less than or equal to 1. So they made a mistake with that. It shouldn't be called P2. It should be called P1. Okay, so it's all the polynomials of degree less than or equal to 1, which is less computation, so it's actually better. So if we're in this world, so basically we're in the world of constant functions or linear functions. These are all either going to be constant or linear. Okay, if you're in P2, you're going to have constant, linear, or quadratic. If you're in P3, you're going to have constant, linear, quadratic, or cubic, and so on and so forth. So here we're only dealing with polynomials that are either constants, where a1 is 0, or they're linear, where they have the x variable. If that's the case, then what's the standard basis? It's going to be 1 and x. That's the standard basis. So every polynomial in this space can be written as a linear combination of 1 and x. That's the simplest kind. But then they give us a few more. They give us, hey, they say this is another set of these two polynomials also form a basis for P1. And so is this one. So I have 3 different bases that are linearly independent and that span all of P1. They span all of it. And so part A asks, find the transition matrix. And I know the notation here is a little different, right? It's like this. This is the same thing as saying, what's the transition matrix from C to E? Okay. So we're going from the bases C to the basis E. What does this mean? C is my old basis, and E is my new basis, correct? Now, how do I do this in general? What's the quote-unquote formula for this? Well, I only have 2 bases, right, to deal with, so I have 2 columns. And the way is that I take the one of the vectors from the old, right? So I'm gonna call this, so if I call this U and I call this V, then what I'm saying is I want to rewrite U in terms of the new basis E. I want to rewrite V in terms of the new matrix, in terms of the new quote unquote basis E. But this is very easy to do. Why is that? Because if I write U, right? If I write U, which is 1 minus x, how would I rewrite this as a linear combination of 1 and x? So like, you see the question here? I'm saying C1 times 1 plus C2 times x. I'm asking what are the constants that I need for 1 and x in order for it to become 1 minus x. And this should be quite apparent as to what those numbers are. 1 and negative 1, that's right. So this is going to be 1. And this is going to be negative 1. Do you guys see that? But then this immediately, what does this give me? It gives me the coordinates relative. This gives me the coordinates of 1 minus x relative to the coordinates, to the basis, the standard basis vectors, which is what? 1, negative 1. So this first column here is going to be 1, negative 1. And the same thing now goes for V. V was what? 2 minus x. Do you guys see what's happening? 2 minus x. So again, I'm going to use another C1. I'm going to call it A1. A1 times 1 plus A2 times x. You know what? Call it something else. Call it B1. B1, B2. So what is this going to be? It's going to be twice of 1 and minus 1x. What does that mean? 2 minus x, when I express this as a linear combination of the standard basis vectors, the coordinates or the scalars associated with that are 2, negative 1. And this is my transition matrix. Does everyone understand this? Is that understood? It may seem like it may seem a bit more complicated because we're dealing with polynomials, and that's a little sometimes maybe a little different than what you're used to with just vectors. But do you see how it's important now? Or do you see how we're connecting vectors to polynomials? The vectors, the components of the vectors are the coefficients of the terms. So the first component of my vector that represents my polynomial is the constant. What's the constant? It's 1. And then the next component of my vector is the coefficient for the x term. Well, what's the coefficient of the x term? -1. So 1 minus x in the world of the standard basis is the same thing as saying 1 -1. It's the same idea. And so that's why doing this transition matrix, finding the transition matrix from this old basis to this new matrix is actually very straightforward. And hopefully you see that B is the same idea, right? What is B? Is the transition matrix from B to E, which is the same thing as saying B to E, right? This is the old to the new. What's the old basis? The old basis is what? 6 plus x. But I want this to be relative to the new. And then the next one is what? -7 plus x. But I want this to be relative to the new. I want to find the coordinates relative to the new basis. But what are the coordinates of 6 plus x relative to the new basis? E, which is the standard basis, is simply going to be 6 and 1. And the next column will be -7, -1. Does everybody see that? So going from creating a transition matrix from one basis to the standard basis is simply writing out the constants, writing out the coefficients. That's how simple it is. Okay, but then what's the issue now? The harder part is when you go the opposite. So for example, when you do this, E to B, now this becomes a bit more difficult. You don't need to do REF. No, not for this. So when you're looking for the transition matrix the first time, oh, I see what you're saying. Yes, actually you can. Okay. Okay. So you can find you can find a transition matrix, right? There's a procedure that we discussed back in I think it was lecture, what is this, lecture like 17 or so. The thing is, okay, so I guess I should mention that there is another way. So the other way of doing it, so this is like, I guess, solution number 1. Solution number 2 is if you use a procedure to find transition matrix. But you'll see that sometimes this is useful, sometimes it's not necessary. So for these examples, it's actually not so necessary to do it, to find transition matrix. Let me just see. Yeah, so the new to the old. So the transition matrix, the way you find it is if you go from the new basis to the old basis. And then the idea is that when you put this in row reduced echelon form, right? When you put this in row reduced echelon form, you get the identity and you get the transition matrix. Do you see that? But the reason why you won't necessarily need to do that here is because what's the new basis? What is my new basis? In this case, it's E, right? What is E? 1x. And so try to just, I know it's kind of weird to do this, but think about 1 as 1, 0. And think about x as 0, 1. Do you guys see why I can do this? I can think of it this way because 1 is in the world of P1, which is the set of polynomials of degree less than or equal to 1. So 1 can actually be expressed as 1 plus 0x, 0 times x. That's 1. And then what is x? Well, x is the same thing as saying 0 plus 1 times x. Do you see now the correlation between these vectors? So if I represent 1 and x as a vector, they're considered as if I'm writing 1, 0, 0, 1. And then what's my old basis? Same idea, right? My old basis here is b, which is what? 6, 1. 6, 1, and then -7, -1. But if you notice, I don't need to do the row reduced echelon form. Why? Because the moment I did this, I immediately had this identity. Identity. I don't need to perform row reduced echelon form. I already get the transition matrix immediately. It's this. Well, in this case, this is C, pardon me. So C is 1, -1, 2, -1, pardon me. This is for B, but this is C. So 1, what was it again? Yeah, 1, -1, 2, -1. So I think the procedure to find a transition matrix for this particular problem might be actually unnecessarily more confusing if you just do it this way. I think this way is just a bit more clearer. And the reason why it's a little clunky at first is because of the idea of polynomials. But once you see the connection between polynomials and vectors, or polynomials and its vectorial representation, then things will be a little bit more clearer. Because I'm treating the polynomial, it's a polynomial, but I'm treating it as if it were a vector, because there's similarities between them. So like I said, the more difficult version of this is if I do the opposite. If I find the transition matrix not from B to E, but from E to B. So now my E becomes my old basis, and my B becomes my new. So it's like, what if I want to go the other way around? What if I want to start with a vector in E with relative to E, and then I want to transition into something being relative to B? Now the long way would be to do what we did here, but it's going to be longer. Why is it going to be longer? So if I were to say I want to write my my old basis, what's my old basis? I got 1 and I got x. These are my old bases, right? I'm going to write 1 and x in terms of my new. What's my new? My new matrix B, right, is 6 plus x and -7. So I'm going to write this. C1 times 6 plus x plus C2 times negative 7 minus x. And I'm going to call this B1 times 6 plus x. B2 times negative 7 minus x. What I'm doing is I'm writing 1, the old basis, in terms of my new basis. I'm taking x and writing it in terms of my new basis. Do you guys see that? And do you see how this now in itself becomes two systems of equations? Because I have this, set 1 equals 6c1 plus 6, pardon me, plus c1x minus 7c2 minus c2x. And then if I combine like terms, I get 6c1 minus 7c2 plus c1 minus c2x. Hope you guys are following this. And then this becomes what? 6c1 minus 7c2 equals 1. c1 minus c2 equals 0 because there is no x here. So it's 0. This is a system right here. Boom. System of equations. You can solve that. And then the next one is what? X is equal to 6b1 plus b1x minus 7b2 minus b2x. Combine like terms and I get what? I get 6b1 minus 7b2, that's the constant, plus b1 minus b2, x, this equals x. But in order for this to be true, 6b1 minus 7b2 must equal 0. And then b1 minus b2 must equal 1. Do you see this? If you solve this system, you get c1, c2, and then that will be the column vector for the transition matrix, the first column vector for the transition matrix. And if I solve for this, I get b1, b2, and this will be the second column. And then you get the answer. So that's like the long, straightforward way. So solution number 1. So solve. This is solution number 1. What's solution number 2? Again, I go from new to old. Row reduced echelon form. And I should get identity, the transition matrix from old to new. Right like this, from old to new. So I could do it this way as well. And now what's the new? What's the new basis? My new basis is what? Well, what are my values here? 6 and 1. So I'm treating it as a vector, right? 6 and 1. And then I'm treating this as another vector, -7, -1, right? And then this becomes what? The old is what? 1, 0, 0, 1. If I take the row reduced echelon form of this, this has to become identity. And then the other side will be the transition matrix. And if you notice, this looks a lot like what? This looks like I, A, and I. And then when you do the row reduced echelon form, you get I, A inverse. So in reality, I already know what A is. What is A? A was what? A was already defined. This is A. So really what I'm finding is the inverse of A. I can find the inverse very easily. And think about it. Remember we talked about this? The transition matrices from an old to a new, compare with the transition matrices from the new to the old, they're inverses of one another. So if I found one, I can find the other one just by finding the inverse. So this question can also be solved by considering it as an inverse. And what would be the inverse? So going back in time, if T from B to E is 6, -7, 1, -1, and the inverse of this matrix is the transition matrix from the other way around, from A to B, what would it be? So again, I can use my calculator to find it, or I can use the formula for the inverse of a 2 by 2 matrix. So what would be my inverse? Did I lose anybody with all? Sometimes I just keep going, guys. If you don't stop me, I'm gonna go keep going on and on. Top row, yeah, top row would be, so you switch the diagonals, right? So you get -1, and this becomes positive. And the bottom is -1, +6, and the determinant of this is just 1. So that's right. So this would be my matrix. So if I were to solve these systems here, if I solve this, yes, you can do this instead of having to solve this system. You can do this. Because this system here, regardless, this system will give you C1 being 1. No, this would give you yeah, this should be -1. -1. Yeah, it is more convenient. But let me just see. Something that I don't think is completely correct. Did I get this right? The problem is that this system, when you solve it, one of them is going to be. Oh, actually, no, they're right. Yeah. So yeah, this should be the same -1, -1. Yeah, that's right. That's right. Because when you plug the -1 here, this becomes -1. This becomes positive. Yeah, this should work out. So what I'm saying is that these numbers here, this first column is the solution to the first system. And the second column, 7, 6, is the solution to the second system. That's what you would have gotten. You would have gotten B1 is 7 and B2 is 6. And if you notice, this works out, right? 7 minus 6 is 1, and then 7 is times 6, right? It's 42 minus 42, so it's 0. So what I'm saying is it's consistent with what we've been doing. But of course, there's less work here. I have to worry less about solving systems of equations, which can be sometimes time intensive, or in other words, just sometimes annoying to do. Does that make sense? So for solving, this is part C. And the rest of the problems the rest of them are similar in nature. And then once you find the transition matrices, you can find the coordinates relative to that new matrix. And so that's how you use the transition matrices. So this transition matrix takes things that are written in this matrix in this order basis, and they rewrite it in terms of this order basis. Does that make sense? So like, for example, if I have a polynomial, right? And my polynomial is 1 plus 3x. So the 1 plus 3x in terms of the old basis, E, would be just 1, 3, correct? And I want to figure out what is 1 plus 3x in my new basis, call it B. What is this? Instead of having to solve the system because I would have to solve a system to get that. Instead of solving it, I already have the matrix that transitions from the old to the new. So to go from 1 plus 3x to the new is the same thing as taking the transition matrix from the old to the new and multiplying it by the column vector that represents the old. Do you guys see that? And there's a lot more letters than usual. But then this is equal to what? What is this? This is -1, -1, 7, 6. Multiply that by 1, 3. And when I do this, I get the coordinate vector the coordinate vector of the polynomial relative to the new basis. So it will equal what? It will equal 20. And then this will be 17. Do you guys understand this now? So 1 plus 3x is equal to 20 b's, 20 of these, 6 plus x's, and then you're going to add 17 of these, -7 plus x, minus x. Does that make sense? So these numbers here are the coefficients of my new polynomial in terms of my polynomial in terms of the new basis. So that's the reason why we find the transition matrix, because I don't want to be solving systems of equations every time I change from one basis to the other. I want to make it much more streamlined and just multiply by a 2x2 matrix. Does that make sense? Does that make sense as to why we care about transition matrices? It makes more sense. Great. Great. So number 6, I hope that's taken care of in terms of how to solve it. I didn't do all of it because I want you to also try it on your own. But the idea, as long as you have the gist of the idea, not just of how to find those transition matrices, but what's the significance of those transition matrices and how we can apply those transition matrices to find the coordinate relative to other bases. Okay. Anything else from here? If not, then I think there's one more question, right? With number 7. It's the same idea. Same idea. So number 6 and number 7 are the same kinds of problem. They're inherently the same problem. It's just that one of them deals with, one of them deals with the polynomial space, and the other one deals with the matrix space. So first of all, the vector space V is this vector space of what? Vector space of upper triangular 2x2 matrices. So what does this look like? What does this look like? A vector space in V looks like a 2x2 matrix A, B, C, 0. And A, B, C are real. That's what this matrix looks like. The lower entry will always be 0, but everything up here can be something else. Could be something other than 0, being non-zero. But this has to be 0 to be considered upper triangular. Okay, and so then we're given 2 different bases. One of them is -1, -1, 0, -1. The next one is 0, 3, 0, 4, -1, 0, 4, 4. Now it makes sense. It makes sense that your basis for your vector space, for this vector space, is only 3 matrices. There's only 3 because the dimension of this vector space is only 3. And why should it be only 3 if you're dealing with a 2 by 2 matrix? Why is the dimension of V 3? Why does that make sense? That this, yeah, the lower left 0 isn't counted, right? So it's always 0. So the degrees of freedom are only in the first entry here, the second entry here, and this third entry. So we only have 3 degrees of freedom. So it makes sense that the dimension is 3, and it makes sense that the bases must only have 3 things in them. So make sure you're able to understand why it's 3. The dimension is 3. So then everything else makes sense, because now we have 1, 0, 4, 3, 2, negative 2, 0, negative 2, 1, 0, 1, 0. We have 2 different bases, and I want to go from one matrix to the other. I want to go from one transition matrix to the other. Right? Okay. So the thing we had to figure out is, how do we go? So my old base, what's my old? My old is C, and my new is B. So what you do have to do, right, is write the old in terms of my new. So if I call this, I'm gonna call this M1, I'm gonna call this M2, I'm gonna call this M3, right? So I'm gonna find M1 in terms of my new. I'm gonna find M2 in terms of my new, and I want to find M3 in terms of my new. That's the idea behind the transition matrix. Okay. So what is M1? And I'm gonna call this, what should I call this? These matrices here. I'm gonna call it I'm gonna call this U, V, and W. Okay. U, V, W. So I want to figure out what coefficient for U should I have, what coefficient for V should I have, and what coefficient for W should I have, right? So then when I find M1 in terms of my new basis, I should get the column vector C1, C2, C3. Does everybody follow that? Yes. So then M1, what is M1? 1, 4, 0, 3. This is C1. U is negative 1, 0, 0, negative 1 plus C2. V is 0, 3, 0, 4. And then C3, W is negative 1, 4, 0, 4, negative 4. Pardon me, positive 4. Now, when you write this out, as you can tell, the 0, right? The 0 count, this will always be zeros. So we don't really worry about this. What do we worry about? We worry about the first component, the second component, and third component. So what do we have is this. We have 1 is equal to negative C1 plus negative C1 minus C3. And then the next equation is what? 4 is equal to 3C2 plus 4C3. And then the last component, 3, is equal to negative C1 plus 4C2 plus 4C3. And then I have a system of equations. I got negative C1 minus C3 equals 1. A 3C2 plus 4C3 equals 4. And then negative C1 plus 4C2 plus 4C3 equals 3. This becomes negative 1, 0, negative 1, 0, 3, 4, negative 1, 4, 4, C1, C2, C3, 1, 4, 3. So C1, C2, C3 is equal to negative 1, 0, negative 1, 0, 3, 4, 1, 4, 4. The inverse of this multiplied by 1, 4, 3. And if you do that, that will give you the first column of your transition matrix. So this equals the first column. Does that make sense? And then you would have to do that for the second column and the third column. So the straight and long, narrow way, the straightforward way, is to solve 3 systems of equations. And I'm trying to see if there's a way to get around that with matrices. Because again, the idea is that you do the new with the old, right? And then this becomes the identity with the transition matrix from the old to the new. That's like the procedure. It's just that the tricky part here is, how do you represent a matrix? Yeah, how do you represent the matrix as a vector? Now, the reason why it's tricky and it's not so clear is because despite the fact that it's a vector space with 3 degrees of freedom, right? The thing is, how would you write this as a as a vector? We already know the 0 is just going to be 0, so we don't really worry about this, right? But how do we write this? Do we write the vector as 1, 4, 3? Or do we write the vector as 1, 3, 4? So then that's the issue that arises. How do you know which way to order it? And I think the more natural way would be, right, 1, 4, 3, because it's just first column. But then ACD, yeah. I mean, but that's the unclear part of it. Because depending upon 1, 4, 3 or 1, 3, 4, depending upon what you decide, right, will give you two different transition matrices, which will probably just be the difference would have one row would be in a different sequence than the other. So if that's the case, then you can try this. Try doing the new. What would be the new? The new would be negative 1. Try this. Negative 1, 0, negative 1. That's the first column. Then the second column would be 0, 3, 4. And then the fourth column, the third column would be negative 1, 4, 4. And then the old would be 1, 4, 3. And then the next one would be 2, negative 2, negative 2. And the last one would be 1, 1, 1, 0. If I do this, I'll get the identity here. And then what would I get over there? So let's try this. So let me bring out my calculator with this. So instead of having a 3 by 5, I'm gonna have a 3 by 6. And then I'm gonna get -1. Always make that mistake. -1. -1, 0, -1, 1, 0, 3, 4, 4, -2, 1. And it's -1, 4, 4, 3, -2, 0. Okay, and so then when I do row reduced echelon form on this second matrix, math, row reduced echelon form option, matrix A, close parentheses. This is what I get. I get -11, -12, 10, -6, -6, 4, -8, -9, 7. So this is the proposed T2 new. So just to make sure we're not doing anything crazy, right? Just make sure we're not saying anything that's nonsensical here. What I'm going to also do is I'm going to solve this. I'm going to find what this is. So the idea is that this here is represented by this. This is the idea. That this first column here would be the solution to this system. If that's the case, then everything is right in the world. So let me just do that really quick. So I'm gonna edit the B value to be a 3 by 3. And it's gonna be -1, 0, -1, 0, 3, 4, -1, 4. So I need one more matrix. It's gonna be a column vector. Call that C, 3 by 1. It's gonna be 1, 4, 3. So when I perform the matrix multiplication, no, hold on. When I perform the matrix multiplication of the matrix and I multiply that by the column vector C, look what I get. I get exactly that. So that's right. So actually, this is much better, isn't it? Because I only have to perform one thing on my calculator. So do you see how this is actually easier and better? Yeah, it's way much more streamlined, right? But I just had to make sure that this was right. Because like I said, the ordering of those numbers will create a new transition matrix, which will most likely just be a difference in the order of the rows, the sequence of the rows. So what was done here was I represented, as you see, the power of, hopefully you start to see the power of linear algebra, the power of representation. So instead of dealing with matrices, I treated them as vectors. That's very powerful. Because if I say this is a vector, this is a vector here, this is the vector here, I can treat all of these as vectors. So I rewrote this as a vector, rewrote this as a vector, rewrote this as a vector in R3, which were these. And then I rewrote the old one. I rewrote this as a vector, this as a vector, this as a vector. and I created this. So these are my new vectors, which are representing matrices. These are my old vectors basis, which is representing matrices. I perform row reduced echelon form upon this. Boom. I get the transition matrix from the basis, the old basis to the new basis. I get it immediately. Instead of having to do all of this, you see how much time and effort I spent just to write the first equation, the first system of equations down. So this will just give me the first column. Then do the same thing again, get me the second column. And then do the same thing again, and then get the third column. But this was just done in literally one full step, which is nice. So this is in fact a transition matrix. This is in fact the transition matrix from the old to the new. Yes, it would save a lot of time. And then from here, you can, like one of the questions asks you find, so you have a new vector M, right? And the vector is defined as 3, -1, 1 in terms of the old, in terms of this matrix C, right? That's what this represents. This is the coordinates relative to this basis that represents this new matrix M. And I want to find what are the coordinates of that same matrix relative to this other basis. Then instead of doing it all over again, I already have the map. This is the map from C to B. I already have it. This is my map. All I have to do is multiply it by the vector. So I would have to just multiply this entire thing. -11, -12, 10. -6, -6, 4, -8, -9, 7. Multiply this by 3, -1, 1. And this will give me the column vector. Okay, any other questions about this? I hope you start seeing the power of representing different objects in mathematics as vectors. With vectors, we can do a lot. We can manipulate it. We can transform things. We can do a lot once we are able to represent different objects as vectors. It's like a sense of like encoding. A lot of things now are being encoded in vectors. A lot of data are encoded into vectors and matrices. That's why the study of linear algebra is so prevalent, has become so prevalent, in particular with data science, machine learning, all of that stuff, because of the usefulness of encoding information in grid-like structures. So learning linear algebra is an essential aspect, especially for most of you in your majors and careers. Okay, so anything else, guys? Is this clear? Any other questions about this? Is linear algebra starting to make more sense, or is it not? It is. Good. So anything else in here or no? How did you get C to B the fast way again? I got it the fast way because I represented all of the basis matrices, the matrices that are in my basis B and in my basis C, right? All those matrices, I represented them as vectors. Why did I do that? Because I wanted to apply this simple procedure of getting the transition matrix. What's the procedure? You get the new basis, and then you treat them as column vectors. You take the old basis, treat them as column vectors, put them in this way where the new vectors are on the left and the old vectors are on the right. You perform row reduced echelon form, find the row reduced echelon form of this augmented matrix. And what you get is the identity on the left side, and on the right side of this, you get the transition matrix from the old to the new. That's the procedure. But I had to do that to matrices, which is a little clunky, right? It's a little like weird. How do you do that if a matrix such as this has 4 components? And how are you going to treat that in a matrix that, you know, they're telling you it's a 3x3 matrix? Well, the thing is, because it's a vector space with dimension of 3, right? I can treat them as vectors. So I can treat this matrix as the vector A, B, C. And that's what I decided to do. So then I can rewrite all of those bases of matrices as just column vectors, a 3x1 column vector. Yeah, you don't multiply them. You augment the matrix. You take the old with the new and augment it and create a 3x6 matrix in this case. So you've had a 3x6 matrix, and then you find the row reduced echelon form of this 3x6 matrix. You get the identity on one side, which is what's going to happen. So the 3x3 submatrix. How did I do this on the calculator? I did it. I did it here. I took the matrix. I took the matrix A. Look at A. Look what I did. You see that? So hopefully you start to see now like how significant these numbers are. They're just not numbers. These numbers are the column vectors. The first 3 column vectors represent the matrices of my new basis. And then the last 3 columns are representing the basis elements or the matrices of my old basis. So you see, I split it down the middle. The first three columns are the new basis, and the last 3 columns are my old basis. Then I performed row reduced echelon form upon this, and look what I got above. I applied it, and this is what I got. I got the identity submatrix 3x3, right, on the left of that invisible line. There is none. And on the right, you have the transition matrix, which we found. How would you convert the 3x1 vector back into 2x2? What would it be back? Would it be by adding back a 0 to the third slot? That's exactly right. Exactly right. You would just undo the conversion, right? So the conversion from the matrix to the vector world was that I took the first 2 columns, the rows on the first two entries of my first row. I think I went way too far. Hold on. Yeah. So the idea is that once I have this, I can go back. So if this is 1, 2, 3, then the matrix would be 1, 2, 0, 3, like that. Okay. Okay, good. Anything else in this section about subspaces, column spaces, row space, change of transition matrices?
Actually, yeah, I'm still not really sure how the conversion. I mean, I get that it's the first one, the 3x1 vector would be just converted back to 2x2 matrix. But looking at it, it's okay. I'm not sure how to explain it. It's like I found the first 2. I found the vector that gets multiplied. But as for converting back to 2x2 matrix, would it be just those vectors, or would it be a separate set of vectors? A separate vector.
So are you talking which vectors are you particularly talking about? Like, for example, this one here.
M of B.
Yeah. So when you multiply this, right? When you multiply this out, you get this, right? You get a certain column vector, correct? Okay. So if I actually perform that, I'm just going to do that here. So when I actually perform that matrix multiplication, I get hold on. So -11 -6, -8, -12, -6, -9, 10, 4, 7, right? And then the column vector 3, -1, 1. So when I multiply A with B, I get this column vector. I get -35, -35, -39, 33, right?
Mm-hmm.
This is what? This is the coordinates of M relative to the basis B. I don't know if that makes, if me saying that makes anything click in your head. This is not the matrix M. Like if I were to write this as -35, -39, 33, 0, this is not M. Do you understand?
Yeah.
This is not M. This is the coordinates relative to the basis B of M. So if I were to write M, right, what would M look like in the terms of the basis B? It would be -35 of the first matrix in B. What's the first matrix in B? I think I have that. What's the first matrix in B? Hold on, this is number 7, right? The first matrix in B was -1, 0, 0, -1. And then I would have a -39 of the second matrix, which is 0, 3, 0, 4. And then I would have the final matrix, I would have 33 of these, which are -1, 4, 0, 4. Do you see what this information here is actually representing? It's representing the coefficients to the basis B that would give you M. So to find M, perform all of this. Multiply this by -35, multiply this by -39, multiply this by 33, and add them together. And that would give you your original copy.
Okay.
You understand?
Yeah, that makes more sense.
Yeah. So this in itself is also like an encoding of information. So you have an original matrix that's in the vector space V, and you say, you know what, let me rewrite it in terms of this new basis. So your bases, you can think of them as like frames of reference. You're in a space called V, which is a vector space, which is like a reality, right? But then you have different frames of references, frames of references. It's frames of reference. Yeah, you have different frames of reference. One of them is called B, the other one's called C. You're dealing with the same object, but you're having different frames of reference. So in one world, this matrix M, if you refer to it, if you view the world of V in terms of C, this is what it looks like, 3, -1, 1. But if you switch your perspective and choose the basis B instead and look at M through this lens, this becomes the vector that it looks like. Do you see that? We're talking about the same M. It's the same M. It's just under different glasses, different lenses. One of them is called B, the other one's called C. They're made up of different elements. So that's why your column vector will be completely different. They're just different things, but they're based upon a certain basis. And that's what's important. The important thing is that you're dealing now with one object and you're representing that object into different representations with respect to a different basis. And now what we're adding on to this is making that transition from going to one basis to the other basis. And that's why the transition matrix makes its way. So now I can go from the bases C. So everything that's written in terms of C can be now written in terms of B just by multiplying by this matrix every single time. Yeah. So to get the transition matrix, the procedure is you take the new basis and you on the left side of this of the submatrix. So on the left is the new and on the right is the old. Perform row reduced echelon form, find the row reduced echelon form of that matrix, and you get the identity. And on the right, you always get that transition matrix from the old to the new. Yeah, I think this might be the most complicated thing, the most complex thing we have discussed so far is this idea of, and it, it got complicated quite quickly, didn't it? Because probably finding the basis wasn't as difficult, but then as we started utilizing bases and finding vectors in terms of other bases, and then finding transition matrix, that complicated things quite quickly in a matter of a few lectures. So breaking things down to its core elements is an important aspect. So if you don't know what transition matrices are for different bases, then maybe go back to understanding what a coordinate relative to a basis is. If you don't understand that, then maybe you have to understand what a basis is. And then that's how you kind of go into fully understanding certain concepts, is going back to the basics of it and then slowly build your way up so that you can really understand intuitively what in the world is going on with all these numbers and all these different vectors and everything else. Okay, anything else? Number 10 from homework number 8. Okay. So let's take it back a bit. Oh, this is a great question. Yeah. Hopefully, after all of this stuff, these questions start becoming much simpler now when you look at them. In the beginning, it might have seemed a little bit difficult, right? But I hope that now you start to see these things a bit more clearly. So it's saying find a basis for the subspace defined. So I want to find the basis of a subspace, okay? Now it's defined by the equation, defined, and of course your equations might be different, defined by 3x1 minus 5x2 plus 4x3 equals 0. So I'm going to call this subspace. I'm just going to call it, okay? I'm going to call it W. We usually use W for subspaces, right? And W is the set of all vectors x1, x2, x3 such that 3x1 minus 5x2 plus 4x3 is 0. So this, I should specify, this is in R3, right? This subspace is a subspace of R3. Now, you may have not thought about this, but this can be represented as a matrix equation. This is going to be a 1 by 3 matrix, 3, -5, 4. And the column vector is x1, x2, x3. You can treat this as A. And this is my vector x. And this is 0, right? So what are you really looking for then? What is W? W, this subspace, is really the null space of A. Do you see that? We're dealing with the null space because we're dealing with an equation with one single equation, but with 3 variables. Immediately, What do we know immediately? What's the rank of A? Well, if you perform if you find a row reduced echelon form of this, what's the only thing you can do? You divide everything by 3, and you get 1, -5/3, 4/3. Rank of A is only 1 leading 1. There's only 1. What's the nullity? Well, we only have one free variable, right? I mean, we only have one pivot variable, which would be this one here, but we have another 2 here that are free. So there's 2. That makes sense because in your answer that you have to plug in, it's a basis with 2 elements. Do you see why it makes sense? Why it has to be 2? So then from here, look what you have. You have 3x1 minus 5x2 plus 4x3. This equals 0. In other words, 3x1 is equal to what? Positive 5x2 minus 4x3. In other words, x1 is equal to 5/3 x2 minus 4/3 x3. What is x2? Call it s. What is x3? Call it t. So this is s, and this is t. And what are we looking for? What are these numbers? What do these constitute or make up? They make up the x values that are representing the null space of A. It's the null space. So this is 5/3 s minus 4/3 t. This is s, this is t. And then we've been doing this, right? We've been now rewriting these vectors in terms of s and t. This becomes 5/3 1 0 s plus t negative 4/3 0 1. This is where does this come from? This is from W, which is the null space of A. This is W can be now written as the span of these vectors 5/3 1 0 and negative 4/3 0 1. The dimension of the null space is 2. These are linearly independent vectors. So this is the basis. This is indeed the basis. So that's how you find the basis for R3. It sounds more complicated than it is, right? It sounds complicated. Find the basis of the subspace of R3 defined by the equation. That looks crazy if you read it. But then when you break it down like this, then you start to saying, oh, I'm really just finding the null space of a one single equation, a system of one single equation. And the null space of that, that's what you're finding. And then you break it down. So really, it's already given to you. It's just embedded. So hopefully start to see a lot of these things are just rewriting what they're giving to you. They're already giving you the answer, but it's embedded in it. You have to sift it out. You have to sift through it. And the way to sift through it is to solve for x1, write the free variables in terms of other parameters if you want. And then you start to see, oh, I can separate these two. I can express this as a linear combination of two vectors. And so that would constitute as the basis for that subspace. Woo, good. Any questions about this? This is good stuff. If I multiply the vectors by 2, would it still be valid? Now, what do you think? Of course. If I multiply any of these by any number, I create a new basis. So if I multiply this by 3 and I multiply this by 5, right? Then I would get a new basis. I would get let's say 3 by 5, right? So this would be 5, 3, 0. And then this would be by 5 would be what? Negative 20 over 3, 0, 5. This is a new basis. Why is it a new basis? Because they're linearly independent still. And And I'm in a space that has a dimension of 2. So the moment I have two linearly independent vectors in a space that has dimension 2, it automatically will span. It's kind of like it automatically forces its way to span. So if I originally know that my subspace has two vectors in it, and I know that two of them are linearly independent, then they automatically span. So yes. Cool. Okay, good. Anything else here? Anything else in any other questions you may have about subspaces, bases of subspaces, anything? I hope this all has helped clarify any notion you may have about bases and subspaces, because this does become our bread and butter as we start dealing with more complicated things in linear algebra. This idea of bases, coordinates relative to bases, it becomes essential. So we're good. Okay, so if there's no other questions about anything, I just want to,
Actually,
yeah, go
can we go
ahead.
over number 5, setting a vector equal to a basis?
Number 5. Okay, so are you talking about this? So you have like a matrix, I mean a basis of two vectors, 5, 2, for example, and 1, 5 like this.
Yeah.
And then you have another basis, right? 2, 1, 3, 2, right? So you have two bases, and you want to find the matrix P that goes from B to C.
Well, so it's just a transition matrix then.
Yeah, they don't tell you what it is. It's just implied. Yes, guys, that's what you have. That's the whole point. They're not gonna tell you every time, oh, find the transition matrix. They're gonna say it without saying it. They're gonna say, find the matrix such that the coordinate relative to C is equal to this matrix multiplied by the coordinate relative to B. The only thing that makes sense to fit in there, right? The only thing that makes sense to fit here is that P is a transition matrix from B to C. Or in other words, T has B and C. That's the only P that matters. And so then from here, it should be quite straightforward, shouldn't it? The new is what? This is 2, 1, 3, 2. This is the new. Then the old is what? 5, -2, 1, 5. That's the old. Then what do? Find the row reduced echelon form of this matrix. And what would I get? I get 1, 0, 0, 1. I'm going to get that. Why am I so sure I'm going to get this? Because these are linearly independent, right? Whatever I do here to create to row reduced echelon form this, I'm going to get the identity because they're linearly independent. But then the thing is, the row operations that I apply to make this 1, 0, and 0, 1 are not the same that would make this into 1, 0, 0, 1. It's not the same because they're just different numbers. So this would produce whatever that would be. This would produce the transition matrix. Okay. So again, not everything will be always so explicitly defined for you. You have to also sometimes connect the dots yourselves and and fill in the blanks, as they say. Well, maybe the meaning of linear algebra. I don't know about, maybe the life might be too broad, but the meaning of linear algebra might just stem all the way down to the row reduced echelon form. That's like finding the DNA, right? Like your DNA is, people are still trying to see how they can come up with the encoding or the code for the genome of the human genome, right? They're still trying to, I don't know if they have already fully encoded everything, but, or decoded everything. But anyways, all right, guys. So let me just stop here with the recording.